Hey there, this will be a video on Newton's method, and before we get into the actual method itself, I want to make sure we understand what it's calculating, what it's used for, and how valuable it can be for any numerical type of analysis that you might do. So let me show you a graph. Okay, so this is using GeoGebra, and so what we're going to do is we're going to look at this function x cubed minus 2x squared minus x plus 0.5. And let's just say that we wanted to find the zeros of this function. So going back to maybe a college algebra type problem where I'm just looking for where does this function cross the x-axis. So it would be about, somewhere close to maybe that negative 0.7. I also have one over here, maybe a little bit bigger than 0.3, and another one farther along the x-axis. So, okay, if I want to try to find these solutions, one thing that I can do is use Newton's method to help me. And what this does is it says pick an x value that you think is relatively close to your zero. So I'm just so you can see this for demonstration purposes, going to pick negative 1.2. Then it says evaluate your function at negative 1.2. That puts me down here. And if I use calculus and I write the equation of the tangent line at negative 1.2 on my function, my tangent line crosses the x-axis at about this point right here, somewhere close to negative 0.8 or 0.8. Well, that's closer to my zero that I want to find. So do the process again. Use that now as your x value. Find where that x value meets your curve, so your function's value. Write the equation of the tangent line. You're even closer. Now that x value or that zero, where does that meet your function? Tangent line, and then you're almost there. And what you can see is I can use Newton's method, this method for finding zeros, and I can go through each iteration or each step along the process. So if I started with negative 1.2, that was my first initial guess, each guess is going to get me closer and closer to that ultimate zero that I see. And what you'll also notice is that after this fourth iteration here, the numbers are pretty darn accurate. In fact, after the fifth iteration, they're exactly the same. So I don't have to do this process all that many times for it to be very, very accurate. So let's take a look at what it might look like on the right-hand side over here. So if I'm trying to approximate this zero at about 3/10, let's make our initial guess somewhere over here. Okay, so let's just say, and again, if my zero is close to 3/10, I'm not trying to suggest that x equals 1 is very close to it, but for our purposes, we'll be able to see this a little bit better. So if my initial guess is x equals 1, where does that cross your function, or what is my function's value at 1? Write the equation of the tangent line at that x value of 1 to my curve. Where does that tangent line meet the x-axis? Look how close that got me. And then where does that x value meet your curve? Write the equation of the tangent line. We're almost on top of it. I can see that after, 2 or 3 iterations, depending on how accurate you want to be, you are very, very accurate very quickly. So it's a numeric way of finding zeros. So let's take a look at some algebra for a second. So if it's a numeric way of finding zeros, let's talk about what that looks like with our good old point slope form. Y minus y sub 1 equals m, or slope, times the quantity x minus x sub 1. And if I'm finding a zero, that's going to be when y1 is 0. So let's put 0 in. Okay, and that x value here is really any x sub n, and I'll get to that here in a minute, and this is y sub n, meaning that will be the function's value, or a point on my curve. Okay, m, well, what is m really talking about? We kept talking about the slope of the tangent line, so m is my first derivative's value there, so I'll call that f prime of x. Okay, I'm going to divide both sides by the f prime of x. And instead of y, we could absolutely write f of x. That's my function's value over the derivative. And I want to solve this for x sub 1. So I'm going to add the x sub 1 over to the left, and I will subtract that fraction on the right. Now, this x is my x sub n just as it was before. My function's value is the function's value at that guess, etc. X sub n is your guess, which will lead you to your new guess. Okay, so your next step of that iterative process. So this is in a table that I have provided for you in your notes. I just wanted you to see where it comes from. It's really just coming from writing the equation of that tangent line. So m is our slope of our derivative, and since we're looking for a 0, y sub 1 is 0. And then it's just solving for the x sub 1. So that's not necessarily anything new, we're just maybe using it in a different way. Okay, so since I'm saying that we're finding zeros, when might I be finding a 0? Well, if I'm using the original function, I'm looking for that 0, that root, the solution, or the x-intercept. Since we are in the reals, all of these mean the same thing. But what am I getting if I'm setting the first derivative equal to 0? Oh, now I'm getting possible max or min, and I'll call that relative extrema. Okay, or what if I wanted to find a 0 of the second derivative? Now I'm finding a possible point of inflection, right, or a change in concavity. So depending on what function I want to set equal to 0 will depend on what I want to start with. The one last thing I will say here is you can actually find where is one function equal to another to find intersection points. Because how is that finding a 0? Well, you would be using, and I'll just use this as an example, f of x minus g of x. That would be the equation that you're looking for to find the intersection between two curves. Okay, so when you're doing Newton's method, you're going to pick, am I looking for a 0 of the original function? Am I looking for a 0 of the derivative? Or am I looking for a 0 of a second derivative? Am I trying to find an intersection? What am I doing? And that's the starting function for Newton's method. And then since there is a derivative in Newton's method, we do have to be aware that if we're starting, for example, with f prime of x equals 0, because let's say I'm trying to find, a possible max or min or relative extrema, if my starting function for Newton's method is the derivative equation, then here I would have to have the derivative of that derivative. That would then be a second derivative. So depending on how you define this initial function, it could be a first derivative, a second derivative, a subtraction of two different curves, etc. Okay, so let's see how this is going to work. And I just want to point out, here's this table where n is going to be the number of iterations that we go through. X sub n is that first guess that you have to create. And then this table just helps to guide you. What is your function's value at that x value? What's the derivative of that at that x value? And then here's your ratio that we're then subtracting from your previous guess, and that will give you your new guess. Okay, so let's see a few examples in the works. So here's the first example that we'll go through. Approximate the zeros of this function. Use Newton's method and continue the process until two successive approximations differ by less than 1/1000th. So that's our tolerance, and here's our function that is given. So one thing, because we do have modern technology on our side, is I do think we should come up with an educated first guess. There's different ways of doing this. You can use different things you've learned throughout your pre-calculus experiences like Descartes' rule of signs. You can use different curvature ideas and behavior ideas, zeros, all of that to help you graph this function. Or you can also use your technology to help you graph this. Again, I don't think we should just be graphing blindly anymore because we have technology on our side. So I'm going to look at y equals, and I'm going to type in the function 3 minus 2x cubed. And I'm just going to zoom 6 because I don't know what window I was in last. And I'm just looking for approximately where does the 0 look like it is. So this function appears like it crosses the x-axis at about 1. So I'm going to say let's let our first guess be a 1. And then I have to do a bunch of calculations. If you would like to do these calculations on your own, that's fine. I'll do them first on my own for this first row, and then from here I'm going to let my table sort of help me out. So f of 1 would be 3 minus 2, so that's going to be 1. But I do need an f prime. So f prime of x is derivative of 3 would be 0, so negative 6x squared. And so if I put x equals 1 in there, I get negative 6. If I divide these, I get 1 divided by negative 6, but I'm going to need the decimal because, again, I want to make sure that I'm less than 1/1000th in the end, so I want to see these as decimals. So basically, if I want to be accurate to that third decimal is what they're trying to suggest here, then I want to go out to 4 decimals in my work. So if I divide that, I should get negative 0.1667. So this tells you how far away basically you were, right? So my new x value will be my x, right, that I started with, which was 1, minus this amount. So I'm going to say approximately again because this was a rounded value. So guess number 2 here, or iteration 2, should be 1.1667. And this gets to be the point where I say I'm not going to do this anymore, in my head or on my paper. I'm going to let my table help me out. So in my y1, I'm going to put the original function, and in y2, I'm going to put the derivative, and since this was an easy enough derivative for me to calculate, I just calculate it. Otherwise, you can use your n-deriv, your numerical derivative feature. I'm going to make sure in my table set or second window that I'm able to type in values into my table. So I go to independent, click ask. Most of you are probably already have that set. So now it's waiting for me to type this in. So my x value was 1.1667. So my original function, and again, I want to hover over these values because your columns are pretty small, so they're not going to have room to write the whole number. So I can see that it truncates it off, in other words. It's not going to have room to write that whole thing. So negative point, I'm going to round to 4 decimals again, 1762, negative 0.1762. Then for my first derivative, again, I want to hover over that because I can only see 3 decimals and I know it doesn't end there. So now I can see 4 decimals, negative 8.1671. Now I'll divide them. I can divide them on my home screen, or I'll show you a way I can actually have my table, I can have a y3 in here if I wanted to, of what y1 divided by y2 would be. So if I go back to my y equals, I can put that in here, and again, you want the original function over the derivative, so I want y1 divided by y2. So if I go vars, which is kitty corner from your arrows, go over to y-vars, function, hit enter on y1, divided by, and we'll do that again. Vars, go over to y-vars or y-variables, hit enter on function, and now arrow down to y2 and hit enter. and now I have that ratio. So now when I go back to my table, I have a third column in there, after my x of course, of this ratio. So that would be 0.0216 if I round to 4 decimals. And so I'm taking my initial guess in this step, which was 1.1667, and I'm subtracting this off. And what you should be seeing is that you are getting closer every time. First I was off by, negative 0.1667, or a little bit more than a tenth. Now I'm only off by 2/100ths. So I'm going to be getting closer and closer to what I think is this approximation. So this is going to be, and again, you can do this from your home screen. This is where I usually will choose to do these subtractions. So I'm just going to say 1 point, and I can probably do this one faster in my head, but that's okay. 0.0216. Copy that right. 1.1667 minus 0.0216. Yep. 1.1451. So that is my iteration or guess 3. But when I go to my table now, a lot is ready for me. So I go to my table, I calculate 1.1451, and I can look at these values. So negative 0.0030. If I put that into my function, the derivative value, or the red, the y2, would be negative 7.8675. Negative 7.8675. And then the ratio, it appears, this e negative 4, it appears like it's 0, but we're going to write it down. So it'd be 0.0004 if we round to that fourth. So now this is telling me that my actual, or getting closer to my actual x-intercept, or 0, would be this guess, 1.1451 that we started with. Now you're only 1, 2, 3, okay, 0.0004 away. I can subtract this 1.1447, because if you subtract 4 from 51, you get 47. But what I want you to notice is, again, this is telling you basically how far off you were from your previous guess. So in other words, if you rounded these to 3 decimals, you would get 1.145 both times. So this is my x-intercept, if you will, rounded to 3 decimals. And if you wanted to check that, you have this on the graph for y equals. I'm going to turn off temporarily the other two because I don't necessarily want to get distracted by that. But if I go back to calculate a 0 on my graph here, it's only showing the original function, and I can go to left bound, so just to the left side of it, hit enter, go to the right side of it, hit enter, and then get decently close for a guess, hit enter, and I can see that my 0 is in fact, if I round to 3 decimals, 1.145. So Newton's method works. So let's do this again and see how we can use Newton's method to find intersection points. So we're going to apply Newton's method to approximate the x value of the points of intersection, again with the same level of accuracy. So one thing that it's important to note is you do still need to get a first guess, right? So my first guess is going to be approximately that they're intersecting at x equals 3. I did label the line because here's your functions. I did label the line f of x. And that curve there that we'll study a decent amount throughout calculus, g of x, because that's that 1 over x squared plus 1. So it appears my first guess is going to be a 3. But in our y equals, we want to be working with only one function, right? What is your function of x? What is your derivatives in terms of x? So I want to subtract these curves so that I'm looking for a 0. So if we take, for example, f of x minus g of x, and let me just write this up here maybe. So if I'm solving where does f of x equal g of x, another way to do that would be to subtract, for example, g of x from both sides, and now you're looking for a 0. Again, you could have subtracted f of x from both sides, so you could say 0 equals g of x minus f of x. It really doesn't matter. So what I'm going to put into y1 is this function over here. The line 3 minus x, right, which was my f, minus my g. And so I will come over here and change my y equals. And I'm also going to remind you how if you don't need the algebraic derivative, you can actually let your calculator do that for you, which if you went through some of the previous videos, you might already know how to do that. So there's my y equals 3 minus x minus 1 over that quantity. Okay, so now if I don't want to necessarily calculate an algebraic derivative, I can let my calculator calculate a numeric derivative. So if you go math, you have a numerical derivative, math choice 8. And you're going to say, I want to take the derivative with respect to x of y1. So that's that vars. Go over to y bars, hit enter on function, hit enter on y1, and I want to do this right now for all x in its domain. And then I can still say that I want to take y1, so vars, go over to y vars function y1 divided by y2. For that ratio. So now when I go to my table, I'm going to delete out the other x values because those aren't important to this problem. I want to start with x equals 3. So, and if I again hover over just to make sure it's not just not showing me stuff or that it's, rounding, and there I can see that it is in fact rounding, but I would round to the same. I can see what these are equaling. So I'll copy those onto my chart. And then now that I have those on my chart and I can see that ratio is 0.1064, so I'm going to go back to my home screen and say what is 3 minus, just to be safe here, 0.1064. So that should be 2.8936. So this guess will be 2.8936. So my second iteration or go around will be 2.8936. I'll go back to my calculator. I'll go back to my table and I'll put in an x value of 2.8936. And I will write down all those values on my chart. Now just be careful. I'm going to write down negative 0.0003. And then my derivative value is the red, so that will be negative 0.9341. And so this ratio turns out to be real small as well. It's 0.0003. And if you're not sure how I'm getting that, that's because of the e negative 4, so it's scientific notation times 10 to the negative 4. So you take this decimal point and you move it 4 places to the left. So then this becomes 2.8936 minus 0.0003. So this is approximately 2.8933. Now technically this one rounds to a 4 while this one is going to round to a 3. So I would do one more iteration just to be safe here with the 2.8933 and to see where we end up with that one. So you can pause and try to do this on your own if you'd like. Otherwise I'm going to fill this in for us. And so once I fill that in for the 2.8933, I did actually have to go out to one additional decimal, otherwise this is going to look like 0. So this will become still the 2.8933. So if we were rounding to 3 decimals, I would say this intersection is at approximately 2.893. So let's just look real quick here at this last example of why Newton's method fails. Now it doesn't mean that we can't use Newton's method, it just really means that the values that you chose are not going to work. So let's take a look at why. So if I have this function right here, which is a third degree polynomial, I've kind of sketched it off to the right there for you. And let's see why if you use 1.5, which is that guess up here, why does Newton's method not work? So my first guess is 1.5 or 3/2. And so again, now if I go back to my calculator, the nice thing about putting in the derivative as a numerical calculation and this ratio as a general y1 over y2 is that the only thing I have to change out is y1 each time. So this is 4x cubed minus 12x squared plus 12x minus 3. And then I can go to my table and everything should be ready to go for me. Again, I'm going to delete, delete, delete because those are values that I don't need. I need to talk about 1.5. Okay, so let's see here. If I evaluate my function at 1.5, I get 1.5, then 3, and then 1/2. So when we divide this, we end up getting 1/2. So really, my second guess should be a 1. So my second guess, I will use a 1. And I can usually calculate pretty quickly here without using my calculator with a 1. So I'm going to calculate this derivative real fast. Okay. So my function value at 1 would be 4 minus 12 plus 12 minus 3. So 4 minus 3 is 1. My first derivative at 1 is going to be 12 minus 24 plus 12. So 24 minus 24 is 0. And this ratio becomes 1 over 0. What you might have found if you did it using your calculator is something that looks like this. So it calculated the original function correctly at 1, but then it's basically trying to tell me that that's 0. And so remember, this ratio is kind of telling you how far you're shifting that over, because that's what you subtract from your x value to get your next guess. Something as big as 250,000, there's no way that we are 250,000 away from our guess. So if you were using your calculators, that's that idea that 1 over something really, really small is really, really big, right? So it's telling me that this cannot be calculated. So what happened was, oftentimes if our actual is too far away from our guess, or if we have a turning point, which I do, in between there, it might not give me the results that I want. Now, if my actual was in between 0 and 1 like that, and I'm guessing something like 1.5, I'm pretty far away. If I guessed something like 1/2 to start with, Newton's method would have worked. So it doesn't necessarily mean that Newton's method won't work for any value. Newton's method just failed for the value that you chose. So you just have to be careful that you're picking something decently close. I hope you found this helpful on Newton's method.